Bom, então vamos continuar aqui. Ainda tem mais algumas de evaluation e depois a gente vai olhar as projeções. Sorry, I'm talking Portuguese. Sorry. Only to get a feeling of Portuguese. So we will continue with the evaluation of some of the variables, and then we will talk about the projections, okay? So here I am showing the CMIP5 results of radiation, and one model that is the same model that I showed before of a French model. Only to show some common aspects. So this first one is shortwave radiation. So it's the radiation which reaches the surface from the solar radiation. And then this is the error, okay? Or the difference between the observation and the model results. And we see that there is a positive difference in these regions, you see, and negative in these IPCC regions. And the same happens in this model, the individual model. This is why I told you that some models can behave very close to the multimodal. Some of them have some greater errors or less errors, but the general configuration is very similar. This error has been associated with the clouds, because in these regions of west side of the continents, there are clouds, low-level clouds, that they are not very well represented in models. So there is more radiation reaching the surface because the clouds can get too much of this radiation in the model. This is why the difference is large in these regions. And in the IPCC regions, there is an excess of clouds. And then there is less radiation reaching the surface. So in one side, in one place, there is excess of radiation, and in the other side, there is underestimation of this radiation. And this is related to the clouds, the errors in the clouds. This is why we need to analyze all the features that affect radiation. And one of the features is the cover of clouds. The other is aerosols. And then the sea ice extension. If there is an extension of sea ice that is not well represented in the model, then the albedo, the reflection of the solar radiation will be different, and then this will affect the radiation and then all the other variables. And this second is long-wave radiation. And all these radiation here are considered as the downwards radiation for the positive sign. So the long-wave radiation is the radiation emitted by any surface. If you remember the Stefan Boltzmann equation from your college or your first physical knowledge in the school, remember this black body radiation equation, Stefan Boltzmann equation, that everybody is emitting radiation. And this is upwards. So all the values here will be negative because it's upwards. So when we have this positive here, this means that there is less wave radiation emitted by the surface because the real will be greater than the model. Okay, and this is the same places where there is the intertropical convergence zones, where there are clouds. So the models are representing more clouds or high clouds in this region than the real. Okay. So now let's look the dynamics of the atmosphere. And here I got this results of this French model. And here is the zonal mean, zonal wind. Here is the equator, north hemisphere, southern hemisphere, and here is the vertical structure. So the temperature, this is the temperature and this is the wind. The temperature and this shading is the bias. So the negative bias is where the temperature is less than the observed. And then the models are showing an underestimation of temperature at high levels, and a little bit of overestimation over near the polar region here, Antarctica, that has some errors in this region here. É bom, né? Como que estava antes?
Eu acho que você quer que desligue a luz?
Pode. Eu acho que é bem. Melhor assim? Mas para olhar lá? É pior? É? Não sei. Ah, ok. Deixa... Eles acham melhor. Mas fica melhor? Is better or worse to see? The same? Yeah, so... Okay. If we look at the zonal wind, here is the same. Equator, north hemisphere, southern hemisphere. And we can see the jet stream here and here. And in the southern hemisphere, we have another jet in the stratosphere that is in this region here. And the model can reproduce very well this kind of structure. And this is one interesting thing, because almost all models can represent the circulation well. The dynamical part of the models are very well represented, because you don't have the physical process that are the most difficult variables to represent. So For example, I am showing here one example of one model that's Hadgen 2, only in the sectors of America, only to show how the model represents. For example, the model is here in January, and here is the era interim reanalysis. And we see that the main features, this is the 850 hectopascal, that is the low-level winds. And the model can get the main features, which is this turning of the wind here in this region, and the heights, the subtropical heights. And here is July. We can have, we can compare and see that many features are presented here. And this is at high levels. This is the Bolivian high. For those who lives in South America know very much about this high and the trough in the Atlantic Ocean. And here's the model, and this is the observation. And the model can reproduce very well in the westerlies, in the here in the winter time in the South Hemisphere, and here in the North Hemisphere, this high in Mexico region. So, as I told you, the model can represent well the circulation. But other features, for example, here I'm showing the dust and optical depth for this Hadgen 2 as well. And the pattern is very well compared with the observed pattern. That there are, the dust concentration is large in this region here, that is Sahara, very close to Sahara desert. And there are lots of dust going to the atmosphere. And also here and in the Australia region. And in this graph, these crosses here are the representation of the optical depth. The optical depth is the related to the concentration of the pollution in the atmosphere. So if there is too much dust or pollution in the air, this depth is large as well. So here's a comparison of the model here and the observation here. And if these results are close to this line, so the model is very similar to the observation. And we see that this crosses here in several, the measure in several places is not so bad, but it's not here in this line. But these stars are in the Atlantic concentration. Now it's concentration, not optical depth. And in the Atlantic, you see that these are, in some regions, are very close to the line. And in the Pacific is squares. This is squares here. This is very close, but this is too far from this line. And the diamonds, that's this here and here and here, is in the Southern Ocean. So this is one way to compare and to evaluate the dust in the models. Another thing that is important to know is the physics inside the clouds. For example, we know that at high levels, the clouds have ice and also water vapor that can change to ice. In the middle atmosphere, we have liquid and cloud, liquid and water vapor as well. But in the low levels, we have only water vapor clouds. This is what I told you about the Taylor diagram. And this Taylor diagram, we have three kinds of evaluation. The correlation, which is in this, which goes from 0 to 1. And so the best correlations are in this side, close to this axis. Here is the standard deviation. We can see here the standard deviation is 1 for the model and 1 for the observation. And these green lines are related with the error, root mean square error. So, for example, let's say this point here. This point here has a correlation of 0.6, and the standard deviation is less the observed standard deviation that is in this line, and has an error that is between these two lines here. And then we see that if one point is close to this correlation, that is 1, and is close to this standard deviation, that's 1 for both, and is in this region here with small error, so we have a good representation. Yeah, Taylor diagram. And this first here is for ice in the clouds. This one is for liquid in the cloud. And this is for water vapor. And this black here is the observed, and the CMIP 5 is this hole here, the circle that's not a solid circle. Yeah, you see the observation is here. The observation has no error because it's compared with the same set of data. The correlation is 1, which is here, and the standard deviation is in this circle here. And here is the CMIP 3, and CMIP 5 is this circle that's not filled. Okay, so if we look at the 3 of them, which one do you know that is better represented by the models? The ice, the liquid, or the water vapor? Water vapor, yes, yeah, that's right. Because all the models are very close to this, the mean, the ensemble mean has almost 990 correlation, and the error is small, and the standard deviation is very close to the standard deviation of the observed. But if you look the ice, the multimodal is not so bad, but it's not so good as the water vapor. So here we can see that there are some problems in the clouds that need to be considered and be developed in new schemes. And here is the same analysis, I'll pass very briefly because we don't have too much time. And water vapor. Yeah, this is another kind of analysis. I'm showing you some different kind of analysis to do evaluation. And this is very nice as well, because it is done one score of performance. There is one equation that shows this, that is in this Jiang et al. Paper. And the worst models are these with red colors, and the best are the greens. So and here there are each of one is with ice vapor in very high, 100 hectopascal, very high in the atmosphere. This is 215, and this is 600, and this is 900. And here we can see the mean, the spatial mean value, the variance, and the correlation. Okay, and we see that the ice is the worst. We already had seen in the other Taylor diagram, but here we see that the mean and variance, well, they are very bad here. And in the water vapor near the surface, all the models can represent well. Okay, so this is another way to show. Now the sea ice extent, that is important things to know if the models can represent well, because we know that with the climate change, with the warming of the atmosphere, the sea ice of the Arctic is reducing, and we need to know if the models are doing well with these projections. So we see that this is the red is CMIP 5, and the black is the observed. So the variability is okay. There is a little bit of overestimation in some months, but the variability is okay. Now we will look at the extremes, and the extremes also are important to know if the models behave well, because we need to know in the projections how would happen in the future. And here is the observation, and here's the model. And this is only to compare visually that the pattern looks the same. We see here negative values in these regions, the minimum, and here is in degrees, and the models can represent well. And in this region also, the T-mean, minimum temperature and maximum temperature. We see that there are regions where we don't have information that is in white. I don't know why. Well, in Amazon it's very difficult to have stations that measure point by point here. But in Northeast, I don't know why they didn't plot in Northeast, because there are lots of information. Well, anyway, and here the trains. The trains is very well captured by the model, and now the colors here are different from the other colors, because here this red and yellows are from reanalysis of INCEP, and the blues are reanalysis from ERA 40 and ERA interim, and the CMIP 5 is this black. Okay, only to change the the colors. And then the model is underestimating the minimum value, or it's overestimating, because here are negative values, okay? But the tendency is the same. And here is the minimum of, here is the anomalies. The anomalies of the minimum, or this means that the minimum temperature is increasing along the time. In the past, the minimum temperature was maybe 16, and now is 14, or negative. But this is for all the globe. There are some papers that analyze each region, but here I'm showing the results for all the globe, only to give some feeling what is happening. And the maximum, for example, the reanalysis of NCEP is doing some silly thing here. NCEP 1 that is not taking anymore for studying. And here is the CEMIP 5 result. That's the maximum is increasing as well. We can see by the anomalies that is increasing in very, very much in the last years. And related to the frost days, which are the days with temperature minimum less than 0, they are decreasing the number of frost days and the number of tropical nights. Tropical nights mean the temperature, the minimum temperature greater than 20 centigrades Celsius. So this is observation and the historical simulation in the period that we have observations. And here cold nights and warm nights. And cold nights are decreasing and warm nights are increasing. So this is comparison with the observations. And also cold and warm spells. Well, I'll run a little bit now because we don't, maybe this is the last of verification or evaluation. And I like this kind of figure. It looks like very complicated, but it's interesting. Because here is each of these squares represent 4 sets of data. So one that is in this left side triangle is the model. The right is era interim. The top is the NCEP 1, and the bottom is NCEP 2. So they are comparing the model, the multi-model, with 3 reanalyses. And if and this is the model, each model compared with the average of all models, the error of all models. So the red colors show the models that have larger errors than the average of all models. And the blues are the models that have the smallest errors compared to the average. So here is the models. Each column is the model, is one model, And here there are all the indices of extremes, precipitation and temperature extremes. Okay? And here is the ensemble mean. So in these two columns, ensemble and median, we see that when we get all the models, so we can get less errors than when we get each of the models individually. And depends on the index as well. Some index are better represented than others. So this is one nice figure to analyze as well. Well, let's go to the projections. And, so here, I don't know if in the first day Marengo talked a little bit about this RCPs. Yeah? Oh, nice. So you know already this. You know what is 2.6, 4.5. So I can go to the other one. So. And you know that 2.6 is the lowest radiative concentration, so is the best scenario we can have, and 8.5 is the worst. And here I will show only these two in this first pictures. And here, global, and this is the temperature change for all the semi-5 models. And the period is this one, 2081 to 2100. And compared to 86 and 2005. Okay, these were the two periods taken in semi-5 and the assessment report. And we see that in 2.6 the situation is bad. Because there are some places, for example, in these regions here, where the temperature can reach more than 3 and 4 degrees above this period here. But look at this 8.5. It's incredible. We can reach here 5 degrees above this period. And look at this. So it's terrible. And one thing that is interesting when we compare with precipitation, these are the precipitation changes in 2.6 and 8.5. And these hatches means the regions where the standard deviation is larger than the difference. So we can say that these changes are within the natural variability. We can't say that it's caused by the changes in the temperature. But there are some regions, for example, this that's not hatched. So in these regions, the standard deviation is less than the difference. And in 8.5, we see that there are many regions, for example, here in the north. This is annual, okay? In the report, in the atlas that I made available for you in the site, you have 4 seasons as well, because there are differences in seasons. The changes are different in each season. But in annual, we can see that, for example, south of South America, there is a positive change in precipitation, and here in the north are a reduction of precipitation, And here is June, July, August. Sorry, this is, it's not annual. I put here only 2 seasons, December, January, February, and June, July, August, where we can see the differences. But there are other regions, for example, this east side of Africa that someone asked about. There is a region here with an increase of precipitation, and also in the north part of Eurasia and North America, and also in the IPCC regions. And well, there is one exercise or one that I intended to do at the end of the lecture. I don't know if we'll have time, but if not, I will give you the questions or the draft to analyze more in detail, and with the atlas information, you can answer, and you can look your own region. Okay. And this is related to the seasonal sea level pressure, and for 3 scenarios. This is 2.6, where we can see that only in this region we have the changes greater than the standard deviation. What is good to know, because as I told you, this region is a very active region. We'll talk about this tomorrow. And this is for 4.5 and 8.5, where we can see that there are many regions in the southern hemisphere and also in the north hemisphere. But here we see that there is less, the pressure will reduce in the projections near or over Antarctica, and increase in this belt of the middle latitude. And this is influencing one of the modes of variability that we'll talk tomorrow. It's the southern annular mode. And in both seasons, we see this kind of impact. And what about the soil moisture? There will be in the projections, it's showing, here is the reds and the yellows are showing a reduction of soil moisture, mainly in these regions here. Here 2.6, 4.5, and 6, and 8.5. And you see 8.5, many parts of North America and tropical South America, and also Europe and South Africa. There is a projection for a reduction of soil moisture. And soil moisture is important to give evaporation to the atmosphere and to be part of the hydrological cycle. And the humidity, relative humidity change, there is a change, a positive change over the oceans. And because with the heating of the oceans, there will be more evaporation and more humidity close to the surface. I don't know if Marengo showed all these pictures. I don't want to repeat, but maybe some or not. And this is related with the cloud fraction change. So how the clouds will change in the future for more or less. So in this region here, we see a reduction of cloud fraction, and in other regions, we see an increase of cloud fraction. And you see that when you go from the scenario 2.6 to scenario 8.5, everything is increased. The influence or the impact is increased, as we should expect. And the sea ice, what is the changes in the sea ice? So it's obvious if we have more, if you have higher temperature, there will be less ice in the sea because the ice will melt, and the models can show this. And this part is the observation that and the models, and we can see that the observations are showing this reduction, and these are the scenarios, the reduction in the scenarios. The first one, 2.6. This the other one, 4.5, 6, and 8.5. That's the worst. And this is the north hemisphere in February and September. This is the southern hemisphere, and in both hemispheres, the sea ice, the projections are for reduction. And if the ice is melting, this means an increase of sea level because the water is going to the sea. And then there is these projections of increase of the sea level. This is global mean for 0.4, that is 40 centimeters for the 2.6, but here is the mean, ensemble mean, that's maybe 70 centimeters, and this is the dispersion of the members. So this is measures the uncertainty in the model results. Okay. And what about the SST changes? Here I got only one season, March, April, May, to show the shadings, the colors are this period of 80 to 2005, and the contour are the future period. So we can see, for example, this color here is 26 degrees. And this line is 30. So this is between 28 and 30. That is maybe 29. So there are 3 degrees more than this period here. And we can see that in all the regions, we can look and see that the sea temperature, the sea surface temperature is projected to increase. And this is only for the North Atlantic, in this 60 west to 40 west and 20 north to 40 north, and only for Hadjen 2, where we see this increase from the historical period to the future. And for all the seasons, we see these changes. Okay. And what about the extremes? So we have here the coldest minimum temperature, and here is the projections that tends to increase, because the observation we already have seen in the other maps that the observations show this increase in minimum temperature. And the projections are for this continue to increase. And the warmest day maximum temperature also increases. And this, the 2.6, we see that there is not, well, increases but then stabilizes, because you know what this means. This scenario, there is an increase of radiative forcing up to 3.1 and then goes down to 2.6 and stay like that. It's different from the others that it continues to increase. And these are the frost days. That is also shows this reduction of frost days. And the tropical nights continue to increase. So the projections for the extremes are that the extremes will become more extremes, continue to have more and more. Well, so the summary of this are here. I showed some basic concept only because you know that to know the behavior of the models and how the models are built, there's lots of things to talk about. But I gave only some basic concept. And then we saw these CMIP models evaluation represented by some variables. I didn't show every variable also because I took only some examples. And you can see more in this chapter 12 and 9 that is in the site. It is part of the report, assessment report. And we saw some features of extremes that are important also. And the projections, precipitation, temperature, sea level pressure, soil moisture, relative humidity, SST, sea level, sea ice, cloud diffraction, and extremes. Tomorrow, we will see some changes in the storm tracks, in zonal winds, in modes of variability. But today, we will do some discussions about the projections. And here we have people from several places, several regions of the globe. And we will pass one. Well, can you pass this, please? Yeah, one. You take one and take. So we have people from South America. Raise your hand. South America. Okay. And North America, is there anyone? North America, one there. No, two. Okay. Central America. Central America, okay. And Africa, Africa, there are so many regions, but North Africa. North Africa, Middle Africa, and South Africa. South Africa, okay. And Europe, who is Europe? Which, France and what? Russia. And the other from Europe? Which country? West Africa. Okay. Yeah, the middle, I think, West Africa. No. Okay. Everybody got this paper? Yeah. So, I need to. Acho que eu tenho aqui. Não. Is one left there? One left. Can you give me one that sorry, I am without. Okay, thank you. So what we'll do is, well, the first one is one question that everybody can ask or can answer that we talk here. What are the variables that affect the radiation process and need to be considered in a climate model? What do you think that we talked about the variables? Who wants to answer? The clouds? Yeah. Yeah. Clouds? Yeah.
Water vapor?
Aerosols? Yeah. Ice in the sea? Vegetation? Yeah. Land use? Yeah.
The soil moisture?
Soil moisture? Yeah. Yeah. So you see, there are many, many, many variables that affect radiation. And all these processes that are related with radiation need to be considered in a model. I took only this example to show you that it's not only one feature. There are many features. Now, the second is to analyze the annual cycle of precipitation temperature in your region. I'll here that map, and we will look here. Yeah, for example, let's take Central Africa. Central Africa, I think that is it includes East Africa, okay? If you take this here, how do you think that the model represents this annual cycle of temperature? Is this one? Sorry, This is Central Africa. This one. The red is the CMIP5, and the black is the observation. Is okay? Do you think that you can believe in a model, in the multi-model in your region for giving this annual cycle or not? Yes or no? Do you, for Africa, here in this Center Africa, do you think that the model is representing? Yes, yes. Yeah. Here is the observed, black observed, and red is the model. So there is a little underestimation in November, December, but the variability is okay. If you get, let's say, Southern South America, there are lots of people here from South America. What do you think? It's okay. Yeah, it's okay. So, as we talked, temperature, there's no problem with temperature. We can believe in the temperature. So, when we saw that projections of temperature, that the temperature is increasing in all the globe, I think we can have a confidence that the temperature will increase because we can believe in the models. But what about precipitation? Precipitation is a little different because we have, for example, let's say South Asia. Is there anyone from Asia? Okay. Okay, you are Central Asia, isn't it? India. Yes. No, South Asia. Yeah, South Asia. Central Asia is a little bit to the north. Yeah. South Asia is here. So this is the models, and the black GPCP, and the other set of observational data. But from GPCP, what do you think? Is good?
I think the models have captured the phase of the annual cycle, but there is some underestimation. There is some dry biases in the models.
But here, the red is CMIP5, and they had plotted here the CMIP3 as well. The CMIP3 is blue.
Yeah.
And we see that the CMIP3 underestimated, but the CMIP5 is close to the GPCP.
But with respect to other data sets, there is still some underestimation.
Yeah, it's underestimating compared with the other sets. Yeah. So here is an example that every observation data has also an uncertainty that is needed to take into account as well. And for example, Australia. Is there anyone from Australia? Oh, good. I thought there was not anybody from Australia. Well, Australia, what's happening there? Here. January, February, March, and May. No, January, February, March, and April.
The summer in Australia looks like that it's overestimating the rainfall in those months slightly, but not by a lot, depending on the data, the observed data set that you use.
Yeah, but is overestimating a little bit.
A little.
Yeah, but in the other seasons,
it looks very good.
It looks okay. Yeah. Yes, Central Asia has some problems here, with some seasons. So this is only one kind of analysis we can do. Now let's go to the other. Now let's start for South America. Yeah. This is the temperature changes in South America projected by all these scenarios here. And the historical is here that showed an increase of temperature, an increase in all these scenarios. And we already saw this now. Before showing that, what do you know about observed climate change in your country? From South America, who wants to talk about observed changes? What do you know about? Let's say.
Temperature will increase and the precipitation is northeast will reduce and the temperature will increase in all South America and the precipitation, I don't know in other countries, but in Brazil the northeast will reduce and the southeast will increase.
Mm-hmm. Yeah, that's right. We see this in the projections, 8.5. We see all this here, but as I told you, this part is inside, is within the standard deviation. So the largest values are here and here. So reduction in the north and increase in the south. And this is in October to March, and April, September, this reduction extend to all East Amazon and Northeast region as well. Okay. So what about this region? There is someone from Peru or from Colombia, Bolivia? Yeah, this region here, you see, is very close to the sea. And the temperature is increasing in the sea here. And this will affect the countries that are very close to the sea in that area. So in Peru, the projections are for increase of precipitation. And what about Chile? Is there anyone from Chile? Chile? Yeah, what happened there?
I remember when Salida said that the desert is growing extension, is reaching every time is going more to the south. That's I know. No, that desert is it's growing in extension.
This season, October, March. Or what is the rainy season, you said? Is this or this? Yeah, we see that there is, in this region, there will be a reduction, but in the south, for example, here, in the south, there will be an increase as well in the north. In central, in the central Chile, there will be a reduction in the projections. And tomorrow we will see that this is related to the displacement of the storm tracks to the polar region. And this is the regional models. Someone asked me about the downscaling. And these are results with some regional models which show the same features that we saw in the global models, or more precipitation in the south and less precipitation in the north and in the northeast region as well. You see? And here there is a change in humidity flux for explaining why there is so much precipitation in the south in the future. So we see that the humidity flux increase to the region. So here is West North America. Who is in the West North America? West, yeah. So we can look a little bit here. And, well, temperature, I think that we don't need to look very much because it's warming. But what about the precipitation? And this is annual. I just include here the annual. Let me explain. What is this? This column is the 25% in the distribution of the precipitation differences. This is the 50%, and this is the 75%. So to analyze, let's take only the 50% that is in the middle. Let's see the middle behavior, because 25 and 75 are the extremes. And only to analyze, let's look at this part here. So what do you think that, and this is the periods, sorry. This is the first period from 2016 to 2035. This is 2046 to 2065, and this is the last period. So the near-term period, the other period ahead, and this is the last period. Let's analyze this only for simplifying the analysis. What happens in this region? The precipitation is going to increase. Yeah. So we see that mainly in the north part, all these regions here will have an increase of precipitation. And what about the east side? Let's look this here. With the, yeah.
Also, oh, sorry, on the last one. Also, my understanding is that less of the precipitation is going to fall as snowfall. And then the southwest region of the western U.S. is expected to dry as precipitation moves more northward and in a more extreme fashion.
This was one of the intention of this question, to see what information you have before and what you can get from these maps. But it seems you already have some information before. This is one thing that we would like to know from you. And let's go to Central America. Who is from Central America? Okay. Let's look this here. Do you have any information before?
A little bit.
Yeah. So.
Well, in Central America, the projection says that the north part of Central America will be dry, so it suggests that will be a future Central American drought corridor, and also project that Costa Rica it's the turning point of the climate change, such the north part of Costa Rica will be dry and the south will be wet, and also Panama. I don't know exactly why, but I have the hypothesis that if when I study all the regimes of El Niño instead of the non-canonical El Niño Modoki, you can see in the last 3 decades that there are more positive phases than negative phases. So it is continuing in the future. It makes that there are laser strong trade winds in the central tropical Pacific, that it's agree that in the coast of the North American Pacific will be wet. And in Costa Rica and in Central America, when a positive phases of El Niño, it's strong, the trade winds in these regions that is related to the Caribbean low-level jet. If that happens, is the confirmation that this drought will be in a future. So I want to prove that if in a future will be have more El Niño phases, this is why the projection are projected.
Tomorrow we will talk about El Niño.
Okay, thank you.
But you have to see that here I'm showing only the annual, and there are differences in the seasons. And in the chapter 14 of the assessment, there is one section for each of these regions. So you can see there the discussion about these projections. Yeah. So. For the Europe, who is from Europe? There are many, but French people. Who you can? What can you say about what happened?
Globally, what happens in Europe is that in South Europe, Spain, Italy, and all the Mediterranean zone, we will get less precipitation, and we'll get more precipitation in the north.
Mm-hmm. Yeah.
And also, I think there is an influence of the Atlantic. It means that there will be more precipitation in the zone far from the Atlantic. Yes?
Mm-hmm. Yeah, tomorrow we will, you see there is a lecture 2 here, some questions that we would combine with these results to see how can we answer why this will happen. What is the physical mechanism? Because we are seeing these changes, but we want to know why. Yeah, and tomorrow we'll see these relations. Well, let's go to the others. North Africa. So North Africa here, who wants to talk about? There.
Well, in North Africa, the precipitation will be decreased in the future. Nowadays, we will change from the arid regions into the hyper-arid regions. For example, in my country, the total annual rainfall decreased below 200 millimeters per year. And in the future, we expect this to decrease to 100 millimeters per year.
Yeah, so it's already being observed,
yes.
These changes, yeah. In this region here, and in this very north, extreme north, and the southern or Mediterranean area is reducing. Yeah. So the Central Africa, well, here we have east and west, but the east is again the there is who is from this region here. There are many people living here. Here, you. You are living here, West Africa, East Africa, sorry. You? No? Ah, I thought that you lived in East Africa. No, where?
I live in West Africa.
Ah, West. So, here. West Africa. Here or here? Here. So what happened here? What happens here?
Presently, there has been a late onset of rainfall in some years. However, rainfall has been is also inadequate in at times. Let's say in the last 10 years, yeah, rainfall has been very inconsistent. In some years, the most of the years, the onset is late, and the peak periods have changed, and the dry spell has also, the period of the dry spell has also changed. The peak period used to be like June and September. It has shifted by like 1 month, and in fact, it is the rainfall pattern is no longer predictable. But in the last 10 years, perhaps only one major flooding has been experienced. Yeah.
And the warm spells have increased.
Definitely, yes, it has increased.
And we see that well, the projections are for drier conditions in this region. Yeah, and the opposite happens in the east side, with projections of more precipitation here and less precipitation on the other side. And what about the South Africa? There is someone. Who is? Yeah.
I'm going to talk more about the southern Africa part. I think as you go from in the southern region, as you go to from South Africa, as you go north, rainfall is decreasing. It's becoming drier and drier. But I think in South Africa, the coastal areas, rainfall is becoming inconsistent, and I think droughts are becoming common in the coastal areas.
Yeah, and in this period, it's showing a reduction that is above the standard deviation. So, yeah, you're right. So I think that the last one, this is for Central and South Asia.
May I ask you a question? I'm asking you a question.
Indian?
Oh, sorry. I'm asking you a question.
You
said the case in East Africa is the opposite of the West Africa, if I'm not mistaken.
Yeah, the projections are showing less precipitation in the future in the west part, and more precipitation in the east part. The projections.
Okay. But at national level, for us in Ethiopia, we had a projection that is telling us, precipitation is no more increasing. The historical data or the observation shows that, it has been highly decreasing from the 1950 to 2005 that we had at national level. And the temperature is, increasing. Of course, we have, different agroecologies, 5 commonly used agroecologies. So that tells us the precipitation is decreasing, the temperature is increasing. So he told me that, it's going to be the opposite of West Africa. So I'm a bit curious about that. How come that?
Yeah, you are saying that the temperature is increasing.
Mm-hmm.
Yeah, and the precipitation is decreasing in East Africa.
That's in East Africa.
In East Africa.
You said East Africa is going to be the opposite of West Africa.
No, in projections.
Mm-hmm.
In projections of precipitation. This is what we're looking here. I haven't looked at the studies that show the opposition of phases of, for example, one anomaly here means that there is opposite anomaly there. I am not saying this. I'm only looking at these projections and seeing that the projections are showing that there will be a decrease in the west, and increase in the east. But I'm not talking about the observations.
I'm saying why. I'm asking why. Why is in a contradiction between east and west?
Okay. Well, you see that the west and east, the features that affected both regions are not the same. So we have many circulations, for example. We have zonal circulations, we have meridional circulations, and depending on the place where these circulations are, you have more water vapor going to the atmosphere and doing precipitation there. And in the other part, you have a subsidence and then less precipitation because the air is going down and you can't form the clouds. So there are this kind of circulations that probably is related to this opposition.
I think both of you are right. The thing is that at the moment, from observations, we have even recent publications up to 2016 that have shown that rainfall over East Africa is decreasing significantly, actually. But as per the projections, they are showing wetter conditions. The truth is that the CMEP5 models are far away from reproducing the actual conditions over East Africa. So the uncertainty is high. So from what you are showing, that is it. That's what has been produced. Yeah. But the actual sense, the performance of the models is very poor, and the uncertainty is very high. So I think that is it. I think the question you should be asking is that, what are the ways that can be employed to improve the projections of East Africa? One of the studies, if you can check, I think by Young et al. In 2014, it pointed out that the models, the CMEP5 models over East Africa, do not produce the coupling of the land and sea surface interaction. That's why it's missing out in the projection. So the thing is, it's true, the observation, what you have observed over Ethiopia and many other countries, like Kenya, where I come from, Uganda, Tanzania, all the countries over the region, the rainfall is decreasing. The projection are wet conditions, which is far away from the truth.
Yeah, yeah. This is why there is every some years there is a new assessment report, because the models are improving, and there will be the CMIP6 with a new generation of models, and then there will be another evaluation to see what are the places that are very well represented, or the places or the variables that still need to be improved. So it's a continuous development of models. We can't say that these results are finished and we will believe and this will happen. In some places we see that we can have confidence, but in other places you are saying, oh, in this place the models can't represent very well. So we can't say something about, because there are larger uncertainty than in the other place. Yeah. Okay, I think that we have reached the time, but I think we already showed this, and only India that was missing, and here is for India that there are 2 persons there, and we can see here. Do you have another different information about the increased precipitation or not?
Here I can see the increase in rainfall, and I have also done a similar study in my paper, and I have also found that in the most of the region of India there is a increasing projection. So it seems correct to me.
So he is agreeing with the projections. And about Indonesia, and this region here, Indonesia, it seems that only in the west part of Pacific there is change. There are changes above the standard deviation, and all this region here, even in the last period, have uncertainties with the present models. And Australia, there is one person there. I think this is the last one.
My arms aren't that long. Well, Australia's a very dry country as it is, and what you see in the southwest of the country, already there are signs of global warming, and the projections are showing that will deteriorate, and there'll be less precipitation. Also, in the north-east, Queensland, where it does rain a lot more, the projections show that will decrease dramatically as well. But in general, all of Australia, the projections show decreasing rainfall.
Mm-hmm. Yeah, we see this here. Although we see that maybe there are more uncertainties among the models, because large areas are below the standard deviation change. Yeah. Here is red. Okay. So I think we will finish now, and tomorrow you can bring this paper tomorrow. And yeah.
Maybe do you have slide about Siberia? I think I saw the slide about Siberia.
Yeah.
Can you show? Because I can tell a little bit. This is area.
Yeah, I asked, where is this?
But Siberia, this is not European part. So this is Asia. Yes. This is area of my research, and so I know that for last 48 years period was revealed the significant growth of annual mean air temperature for 2.5 degrees due to increase both in summer and winter temperature, but contribution of winter warming was in 2 times greater than the summer warming. As well as was reported the significant degradation of the permafrost for this period, the significant growth of the carbon dioxide efflux, and for last 5 years period was revealed the significant that precipitation decreased significantly for last 5 years period. And so I think that in the future, also the carbon dioxide, the efflux will be increased, and the precipitation will be decreased.
Mm-hmm. Oh, thank you. Sorry, I was trying to find here. Here, maybe no. It's yeah. I don't know where it is now, but yeah. But then this question, this information of permafrost is a very, very serious thing, because with the higher temperatures, all that carbon will be released in the atmosphere. And it now is there, frozen. But if this is released, it will be lots of carbon going to the atmosphere. So we need to keep the temperature in the 2.6. Please do whatever you can to keep this. Use less petrol in the cars. In Brazil, we have alcohol cars from, fuel from alcohol, not petrol. And maybe other parts of the world could do this as well. And less pollution and less energy spending And you know, you are the new generation. You will try to keep the temperature down. Okay? Okay. Have a good trip. Well, I'm going with you to the hotel. Okay? Thank you, and tomorrow we'll continue.